Okay, great. Yeah. Thank you for attending this, I think, last talk of the workshop. And I'm going to present this work framework for high throughput sequence alignment using real processing in memory systems. This work has been led by Safa Diab and Professor Izzat Elak from the American University of Beirut. And yeah, we have collaborated with them. It's something that has been published in Bioinformatics this year. And as you can see, there are a couple of archive versions that are available, and also the source code is publicly available. So let me start with some quick executive summary. First of all, genome sequence alignment is typically memory bound on conventional processor-centric systems like CPUs and GPUs, and processing in memory has the potential to overcome this data movement bottleneck by placing compute capabilities near or inside the memory arrays. In this work, we present alignment in memory, which is a PIM framework for genome sequence alignment on general purpose PIM systems. AIM, or alignment in memory, supports multiple alignment algorithms like Needleman-Bunch, Smith-Waterman-Goto, GenASM, and the wavefront algorithm, and it's implemented for the AACBB PIM architecture. Our evaluation, as you will see, shows that sequence alignment on PIM can be significantly faster than on CPUs and GPUs. This is an outline of this talk. First of all, I will start with a little background and motivation, why sequence alignment, also regarding sequence alignment on CPU, and then I will talk about processing in memory as a way to alleviate the data movement bottleneck. Next, I will present AIM, the framework for sequence alignment on PIM systems, and finally the evaluation. So let's start with the background and motivation. Sequence alignment algorithms like Needleman-Bunch, Smith-Waterman-Goto, GenASM, or the wavefront algorithm, and I think that they are used to align different sequences, might be text, might be something else. In the context of this workshop, they are reads and references, and I think that there is no need from my side to introduce these algorithms here. But there is a need, I believe, to motivate why we need or might need PIM for these kind of algorithms. And here you can see some motivation results, alignment on CPU. This plot shows execution time for the 4 different algorithms, and actually 2 different versions of the wavefront algorithm. As you can see, 4 different number of threads from 1 to 48. And one common observation is that the performance tends to saturate as the number of CPU threads grows. And that's not only happens on sequence alignment on CPU, it happens on many other applications, on many different domains, but in particular, sequence alignment is not very much compute intensive. It has low arithmetic intensity, so it makes sense that this happens. But we can go even further and do some more analysis of different metrics that we can gather with profiling. For example, instructions per cycle. As you see, as we increase the number of threads, the instructions per cycle decrease. And what this means is that the CPU is wasting time. There is idle time because threads are waiting for something. And in particular, they are waiting for data coming from memory. That's why we observe as well that the memory stalls increase as we increase the number of threads, because threads are waiting for data from memory. So this is why processing in memory makes sense in this context. And we are going to pose processing in memory as a way of alleviating the data movement bottleneck for these workloads. I'm pretty sure that all of you are already familiar with processing in memory and with the AACBB PIM system that we have used in this study, because there have been other talks in the workshop, but I'm going to very briefly give an overview. First of all, in conventional CPU processing, the problem that we have is that the access to memory behaves like a funnel. So all memory accesses from the cores need to go through the same place, through the same narrow memory bus. When we use processing in memory systems, each PIM core has access to its own DRAM bank, they have direct access to memory. That's why latency is much shorter and bandwidth is, the aggregated bandwidth is much larger. And in this work, we are considering PIN systems similar to the ones that are already real, either as commercial systems or as prototypes. And we have observed that among all of these, there are some common characteristics. The first one is that there is a host processor that has access to a standard main memory and PIM-enabled memory. There is a PIM-enabled memory that contains multiple PIM processing elements with high bandwidth and low latency memory access. The PIM processing elements run at only a few hundred megahertz and typically have a small number of registers and small caches if they have caches. And finally, they usually need to communicate via the host processor, which might entail some important overhead for some workloads. Luckily, it's not the case in the workloads that we are targeting in this work. A state-of-the-art PIN system looks like this. As you can see at the top, there is a standard main memory, or the host processor that we have here on the left-hand side has access to the standard main memory and the PIM-enabled memory. And PIM-enabled memory is typically composed by memory banks and nearby cores or accelerators or something else. In our work, as I said earlier, we are going to use the AACBB PIM architecture. This one uses, or the PIM cores are general purpose processing cores that are called DRAM processing units, or DPUs, and they run up to 24 PIN threads that are called tasklets. And they support 32-bit integer arithmetic, but multiplication and division are not supported natively. They are emulated, same as floating point operations. The good thing is that this is not important for the workloads that we are targeting in this specific work. Each PIM core has also access to its own DRAM bank of size 64 megabytes in the current generation, and its own scratch pad that is called WRAM of size 64 kilobytes. The DRAM bank is called NRAM, and I'm clarifying this, or I'm mentioning this because in later slides you will see NRAM and WRAM in several places. Okay, so let's talk about alignment in memory, this framework for sequence alignment on PIN systems. Supported algorithms are the ones that I showed earlier: Needleman-Bunch, Smith-Waterman-Goto, GenASM, and the wavefront algorithm. Actually, two versions: let's say the basic wavefront algorithm and the wavefront, the WFA-Adaptive algorithm. These are the ones that are currently supported, but the framework can obviously be extended to other algorithms, and it could be adapted as well to other PIM architectures with similar characteristics, because the way that we are going to partition the workload, for example, and distribute to the different processing elements and on the PIN side, it would be very similar. So let's take a look at how the framework works. For sequence alignment on PIM systems, we have a host CPU, and the very first thing that the host CPU will do is opening an input file and storing the contents of this file in the main memory. This file is going to contain sequence pairs that we need to align, and we are going to use the PIN system, the PIN cores. Remember that they are called DPUs. So the second thing that the CPU will have to do is send the sequence pairs to the PIN cores, in particular transfer to the DRAM banks, to the NRAM in the PIN DIMMs. And then if we look at each of the DPUs or PIN cores individually, as I said, each of them have a core, but they also have access to their DRAM bank called NRAM and their sketchpad memory called WRAM. So in each PIN core, in this specific architecture, we are going to have different threads aligning different sequence pairs. And this is kind of an embarrassingly parallel approach. So each thread can work in a completely independent manner, and this avoids any inter-thread or inter-PIN core communication or synchronization, and that's that which could represent an important overhead in other workloads. In step 3 of the framework, each thread copies a sequence pair from the NRAM to the WRAM using a DMA transfer, because there is a DMA engine for communication or for data movement between the NRAM and the WRAM back and forth. And next, the threads align the sequence pair, extract the alignment operations using traceback. So because each thread is working individually, there is not, let's say, a big challenge on how to parallelize this, because the parallelization is straightforward in that sense. Challenges arise when we need to manage the WRAM efficiently. For example, when we need to manage the size, the scratch pad, which is of quite small size, in an efficient manner. And we are going to elaborate on that in a couple of slides. So in the next step 5, threads write the alignment score and operations to the DRAM bank via a DMA transfer. And at that point, this alignment score and operations is available or is accessible by the host CPU that can copy the results back to the main memory. And at the very last step, the host may want to write the alignment results to an output file. So as I said, the biggest challenge here is how to make efficient use of the available memory spaces with what we call the data management. And here we explore 2 different approaches. The first one is more straightforward and potentially higher performance because it only uses WRAM. It only uses the scratchpad for the intermediate data structures. When we say intermediate data structures, what we mean here is, like, for example, the dynamic programming table in Needleman-Bunch or Smith-Waterman, or the waveframe itself in the waveframe algorithm. So the way that we are going to use MRAM and WRAM is more or less like this. In MRAM, in the DRAM bank, we find the sequence pairs that have been sent by the host and are going to be processed or aligned by the pin threads, and also the alignment output. And observe that for the intermediate data structures, we only reserve a space in the WRAM, right? So the problem is that the size of this WRAM is of limited capacity, and at some point we might need to do something else because we don't have enough WRAM. So what this basically means is that the fact that the size of the WRAM is limited means that the space that we have for the intermediate data structures is also limited, and this is going to limit either the size of the sequences that we can align or the number of pin threads that we can run concurrently on the pipeline. So that's why we came up with another approach as well that uses WRAM and NRAM for the intermediate data structures. Let's say that the intermediate data structures now reside in the NRAM, which is much larger, 64 megabyte, and we simply use the WRAM as a data cache. And this data cache is loaded on demand. Good thing is that we are not going to be limited by the small size of the WRAM, but the let's say average memory access time is going to be longer, is going to be higher, because we will eventually have to access the NRAM, which is farther away from the core, and that might affect performance a little bit. For WFA and WFA-Adaptive, they use intermediate data structures of varying size. Those are the wavefront components, and that requires dynamic memory allocation. And the AppMem SDK provides an incremental dynamic memory allocator, but this memory allocator is shared by all pin threads. And here, we want all threads work independently. Otherwise, they would need to synchronize. And that's why we design a custom per thread memory allocator for low overhead dynamic memory allocation. You can find more details in the paper. Now let's go to the evaluation. First of all, the evaluation methodology. We have used real and synthetic data sets for the experiments. You can find them there on the slide, and we have evaluated different systems. First of all, an AppMem-based pin system with more than 2,500 pin cores, and also 3 CPU systems with different characteristics. As you see, they have a different number of cores, and interestingly as well, they have also different L3 cache sizes, and that's going to be clearly impactful in the execution time results. Actually, we are going to start the evaluation by analyzing the performance on the 3 CPU systems. Here in this slide, you can see for 2 different values of the heading distance threshold, 1% and 5%. This is the execution time for different read lengths for the 5 different algorithms that or the 4 algorithms with the 2 versions of the wavefront algorithm that the AIM supports. The first or the most interesting observation here is that the CPU system with the largest L3 is the one that performs the best, and this clearly aligns with the fact that these workloads are memory bound. Larger L3 will alleviate the data movement bottleneck more, and that's why we basically observe better performance, even though it's not the system with the highest number of threads, for example. Now, in comparison to the PIN system, this execution time, this let's say yellow or gold bar that just appeared represents the results on the admin-based PIN system, including data transfers. Remember that we have the admin memory and we have the main memory where everything starts. So we need to transfer data from the main memory to the PIN memory or to the admin memory. But the interesting observation here is that PIM outperforms the CPU systems in the majority of the experiments. We see speed ups of up to 2.56 times faster than the CPU for WFA-Adaptive. And we also show in this plot results for the execution time, excluding CPU PIM and PIN CPU transfers that somehow give us a hint of what would be a future PIN system that really replaces, or a future PIN memory that really replaces the standard main memory and would save us these data transfers. And here we can see some impressive speed ups up to 28.14 times faster for WFA-Adaptive. The overhead of these CPU PIM and PIM CPU transfers could be avoided or hidden in future PIN systems, either, as I said, using the PIN DIMMs as main memory, or also overlapping data transfers and computation, which is something that is not possible in the current admin-based PIN system because the DRAM bank, the NRAM banks are accessible to either the host processor or the PIN cores. Now some more analysis. One thing that we observe is that for algorithms with regular access patterns, as is the case of Needleman-Wunsch and Smith-Waterman-Goto, for short read lengths, we see that the PIM does not outperform the CPU, but that's something that we could as well expect, because when you have a small reads and also regular access patterns, the CPU can really take advantage of hardware prefetchers and also the cache hierarchy. So that's why, I mean, in those cases, it doesn't make so much sense to use PIM, because the prefetchers and the caches are doing a good job. But that's not the case for other algorithms. For example, the WFA-Adaptive, which is more state-of-the-art than Needleman-Wunsch or Smith-Waterman-Goto, we see that they have linear space complexity, and that's good because it's unlikely that they will exceed the DRAM capacity, the NRAM capacity. And what that means is that we can go for pretty large read lengths. And here in this plot, you can see execution time for different edit distance thresholds for read lengths of 5,000 and 10,000 base pairs. So PIM continues to outperform the CPU systems for large read lengths, and that happens for all the experiments only when we are in, you know, this extreme case, 10,000 base pairs and 5% edit distance. The scalability turns out to be limited, but in this case is because of the WRAM capacity, because in the end, even though WFA and WFA-Adaptive are very efficient in terms of space, but as you make the reads longer and also increase the edit distance, they are going to require more memory, and the size of the WRAM is pretty small. But there are some software solutions that we could put into practice, not as a future work, let's say. The first one would be to reduce the WRAM footprint by stringing partial wavefront components from the MRAM, and or using multiple pin threads per alignment. Remember that in order to avoid all synchronization between pin threads, we are just assigning one alignment per pin thread. A future implementation could use more pin threads, and in this case, make better use of the available WRAM. And also, hopefully, we will see future or upcoming UPMEM PIM cores with a larger WRAM capacity, which will definitely have a positive effect on these workloads and many other workloads as well. And now for some comparison to GPU, because there are also GPU implementations of these algorithms, we focus here on the comparison to WFA on GPU. And here you can see some summary results. This table is coming from our paper. What we see is that in the majority of the experiments, the PIM system outperforms the GPU. It's not in all cases, but in some cases we can see, well, more than 2.6 times speed up. Finally, with respect to intermediate data structures, remember that we are using two different approaches. One uses WRAM only, the other one uses WRAM and MRAM. And here you can see some results for the different algorithms, execution time with different read lengths between 100 and 1000 base pairs. And there are some interesting observations here. So first of all, is that for algorithms that need large data structures, WRAM only does not scale, because the dynamic programming table is pretty large. So at some point, if we want to only use WRAM, the only thing that we can do is reducing the number of concurrently running pin threads. That's why, as you see for NW and SWG, we can only use either one or two pin threads in the case of NW, or just one in the case of SWG. For algorithms that use small data structures like GenASM, WRAM only is better because data structure is small, so it typically fits in the WRAM. So that's why the WRAM only is better for GenASM. And for those with medium-sized data structures, WRAM only is better for short reads, but for longer reads, we need to go to the WRAM plus MRAM approach, because otherwise the WRAM only approach requires us to reduce the number of concurrently running threads. And as you can see, for example, in WFA, for 1000 read length, we can only use one thread. And that really doesn't make much sense, because we are far from the peak throughput or the peak performance that the PIM cores can achieve. This is basically all. You can find more details in the paper published in Bioinformatics, and the source code is publicly available. We actually have 2 repositories. Just to conclude, the executive summary again, genome sequence alignment is typically memory bound on CPUs and GPUs, so processing in memory can alleviate the data movement bottleneck, and that's why we have developed and present here alignment in memory, a PIM framework for genome sequence alignment on general purpose PIM systems. As you have seen, AIM supports Needleman-Bunch, Smith-Waterman-Goto, GenASM, and WFA, and its first version is implemented on the UPMEM PIM architecture, and the evaluation has also shown quite good promise in comparison to CPUs and GPUs. So that's all from my side. If you have any questions, I'm available, and I will try to answer as much as I can, because I'm the 4th author. but yeah, let me know.
Thank you very much, Juan. Any questions? Well, it was self-explanatory, I guess, or you're explanatory.
Okay, great.
Well, thank you very much again. Thank you.
Okay. Thank you.